You students always ask, why are we studying these topics? I've never seen any of this in real life. Let's start from the beginning. Where and why you'll actually need this model, and where you'll find it applied. This model will help you understand many real-world phenomena. For example, why does oil float on top of water? Why do massive ships, despite their huge size, float and do not sink? Why does wood float but metal sinks? There are many more examples, but in our world, we especially need fluid mechanics in engines. For instance, how water and oil flow inside a car, how cooling systems operate, and how these fluids circulate to keep the engine running efficiently. This gives you a clear idea of why this model is important and where you will need it. Now let's start properly and keep it simple. At the moment, you don't understand much, and that's completely normal. How could you know this if you've never taken a course or asked about it before? So we will begin with something very easy and build up step by step. Let's start with something very simple. Think of a water tank, the kind you often see on rooftops in many places. Of course, it's filled with water. That part is easy to picture. Since this is an open tank, the water inside appears almost still. However, if you observe carefully, you'll notice slight movements. Why does this happen? It's simple. The air pressure above the water surface applies a constant force on the water. This pressure remains stable as long as the tank stays open and exposed to the atmosphere. At this stage, we know that the atmospheric pressure is P atmospheric, approximately 1,325 pascals. The water applies pressure on the bottom of the tank together with the air above it. However, different liquids do not apply the same pressure as water. The pressure depends on the liquid's density and the height of the liquid column. It can be calculated using the following formula: P equals RAO times G times H, where RAO is the liquid's density, G is the gravitational acceleration, H is the height of the liquid column. And that's how pressure builds up at the bottom of a water tank. We've seen how both air and water contribute and how the liquid's density and depth affect the pressure. In the next level, we'll go even deeper and apply these principles with real calculations and examples. Stay tuned.